Okay, so what we want to do is we want to look at our oxidation rules. Now, the oxidation rule that I think is the most helpful as we do these problems, since you do need to memorize them, is that oxygen is 99% of the time, maybe not 99, but the vast majority of the time, oxygen is going to be -2. The oxidation number for oxygen is going to be -2 each. Now, if you notice, there's 5 oxygens, right? And so that means there are 5 oxygen. So that means that the oxidation numbers that come from the 5 oxygen is going to be equal to -10. Okay, now if you notice this molecule right here, it does have a charge. It's no charge. Okay, if there is no charge, that means the total oxidation number needs to end up at 0. Okay, so that means when you add up all the oxidation numbers, they should end up at 0. And if we look at oxygen, there's 5 oxygens, so that's going to be -10 from the oxygens. Okay, now if you notice, there are 2 phosphorus atoms inside this molecule, which means that the 2 phosphorus atoms need to balance out the oxidation numbers from the oxygen. And so if all the oxygens give you an oxidation number of -10, that means that each of the phosphoruses need to be +5 in order for it to balance out the -10. Because again, this molecule has no charge, which means that it needs to have a total oxidation number of 0. So each phosphorus needs to have an oxidation number of +5. Okay, so hopefully that kind of helped refresh your memory on oxidation numbers. Again, I do recommend as we go through the oxidation and reduction stuff for the first half of the class period, that you guys have the rules up on your screen, and then you guys just look at the problems up here, okay? So that being said, I'll give you guys maybe about 2 more minutes. Try to finish C, D, and E. Okay, just keep in mind, again, easy way to do it is oxygen is going to be -2 the vast majority of the time. That'll help you with C and E. And then for D, there's another rule that you're going to have to use. So see if you guys can figure that out, okay? So I'll give you guys about 2 minutes. You can work with the person next to you. Again, I recommend having the oxidation rules on your Chromebook screen, and that you guys look at the problems up here on the board. And then we'll go over it in just a sec, okay? All right, so I'll give you guys another minute to finish that up. If you don't finish all of it, that's totally okay. We're going to go over it, and you guys can always go over it as I'm going over it on the screen. Alrighty, guys. So if you guys are still working on it, no worries. You guys can keep working on it as I go over the problems and just check your answers. But if you are a little confused or if you're done, let's go over it together. Okay, so here we have a polyatomic ion and the charge is -2. that means the total oxidation number at the very end, when you combine all the oxidation numbers, it has to end up as -2, which is the charge on the polyatomic ion. Now, we're looking for Cr, but we have a bunch of oxygens, which is easy because if each oxygen is -2, what's the total oxidation number of all these oxygens together? Yeah, -14. Okay, which means that the chromiums right here, the Crs, they need to balance out the oxygens, but we want to end up with a total of -2. Okay, so we don't want to completely balance it out. We just want to make sure that the oxidation numbers get to -2, which means that these are going to have to add up to 6 or 12. So that means each of them are going to be +6. Okay, so the oxidation number for each of these CRs is going to be +6. Okay, because that way we get to +12. And then when we combine that with the oxidation numbers from all the oxygens, that'll get us to the charge, which is -2. Okay. So I know these are tricky, but we'll be doing more and more examples throughout this class period, and there are some on your homework. So hopefully it gets you guys that practice. Now this right here, SNBr4, this one does not have oxygen, so we can't just use the oxygen rule. However, if you guys take a look at your oxidation rules that I have on your workbook earlier up, you should notice rule 3D. Okay, and if you notice 3D, the BR is a halogen, and what's the charge on the majority on halogens the majority of the time? Yeah, -1. Okay, so halogens usually have an oxidation number of -1. So if there's 4 of them, that means all of the BRs contribute an oxidation number of -4. And so if you guys notice again, this guy has no charge. And so tin has to balance out the -4 by being +4. So the oxidation number for tin is +4. All right, and then last but not least, we have BaO2. Again, we got some oxygens, so we got 2 of them, so it's -2 and -2, which is -4. They need to balance out to 0, so barium has to be +4, okay? So if you guys were able to get all of those on your own, you should be in pretty good shape. You are right, I know exactly what I did wrong. I'm sorry, guys, I'm tripping right now. This is not oxygen. I reminded you guys about this last time, but O2, if you guys notice, this is a polyatomic ion. I'm so sorry, guys. Like I said, chem in the morning is hard, right? Okay, so if you guys take a look at your polyatomic chart, you should notice that O2 can be a polyatomic called peroxide. And the reason why we can tell this is peroxide is because the most common ion for barium is +2, the charge, right? Okay, and so if this is +2, we can't have just regular oxygens here because oxygen's MCI is -2. Okay, but it looks like they're balancing each other out, which means that this can't be 2 of oxygen's MCIs. Instead, this has to be the polyatomic ion peroxide. Okay, and peroxide has a charge of -2. I'm so sorry, guys. I'm totally confusing you guys right now. Okay, and if you guys take a look at rule number 3A, it tells you that oxygen is usually -2 unless it's in peroxide. And this is peroxide right here, so the oxygens here are -1 each. And so barium is going to be +2. I'm so sorry. I know that was really confusing.
I got it right in the wrong way. I thought it was just barium is going to equal like +4.
No, you never want to take a look. You never want to look at the metal first. You always want to take a look at non-metals usually.
Oh, that's what I did first. At least when I saw this, I was like, oh, it's -2. So I did 2 -2 like during saw that.
For sure, for sure. Alrighty, guys. So I know that was a lot of oxidation reduction stuff just to start class with. Does anyone have any questions though about any of the problems up here, A through E? Make sure you guys let me know if you guys have questions because we're going to be doing more oxidation reduction. And it's going to be a little bit trickier. Okay, let us move on then. So right here, or I guess for 410 and 411, we've just been looking at individual molecules, what the oxidation numbers are. However, the important part of oxidation reduction is when we have chemical equations like this. And what's going to happen is on the AP test, they're going to be asking you guys, in a chemical reaction, which species, it's just a fancy way of saying molecule, which molecule is being oxidized and which one is being reduced. Now, if you guys remember that handy dandy acronym, oil rig, oxidation means that it loses electrons, and reduced means it gains electrons. Okay, because remember, oil oxidation is loss, and then rig reduction is gain. Okay, so we have a chemical equation like this, and you're going to see usually two reactants, two starting compounds. And what we're going to do is we're going to be looking at the oxidation numbers of the reactants and the products to find out which one gained electrons and which one lost electrons. Okay, so that might sound kind of weird, but we're going to go through it together. Okay, so if you take a look at the first compound, the first reactant is Mg. Now, if you notice, this is a reactant that's only made of one element, okay, which means this is in its elemental form. And what's the oxidation number of an element that is inside its elemental form? 0. Yeah, if you look at rule number 1, the oxidation number of magnesium is going to be 0. Okay. So magnesium has an oxidation number of 0. Okay, next we're going to take a look at HCl. Okay, so we see H, hydrogen can be +1 or -1, depending on what it's bonded with. Chlorine's a non-metal, so what's the oxidation number of hydrogen going to be? +1, yeah, it's all good. Got the plus. And then that means chlorine obviously has to be -1. Okay, now we're going to move on to the reactant. So we have MgCl2. So chlorine is a halogen. So you guys see how we're kind of combining all these rules together, right, to find the oxidation numbers. Chlorine's a halogen. So what's the oxidation number on chlorine? -1. So on the right side, chlorine is going to have -1. I'll put 2 of them just to show that it's 2 of them, which means that magnesium has to have an oxidation number of +2. And then here we have H2. So this is a molecule only made of hydrogen. So what's the oxidation number for that one? 0, yeah, because it's in its elemental form. I know this is a lot of rules. We're kind of combining a lot of things. But this is why I wanted you guys to have the oxidation rules in front of you. And again, you guys will have to memorize these. Okay, so this problem is asking us to find which one is being oxidized and which one is being reduced. And so what we have to do is we need to take a look at their oxidation numbers and how they change from the reactant side to the product. The reactant side tells you what the oxidation number was before the reaction, and then the product side tells you the oxidation number afterwards. So let's take a look at magnesium. Magnesium started with an oxidation number of 0. And then if you notice, it ended up with the oxidation number of +2. So if it went from 0 to positive, did it lose electrons or did it gain electrons? It lost electrons. I know it's weird because remember, electrons are negative, right? So if you push negative people out of your life, right? If you cut me out of your life, you guys would become so much more positive, right? And so it's the same thing. They're trying to get rid of the Mr. O's, the electrons, the negative things. Magnesium got rid of the electrons, and that's why it became positive. So magnesium lost electrons. Okay, so if it lost electrons, was magnesium oxidized or was it reduced? Oxidized, yeah, magnesium was oxidized. Hey, it's okay, guys. If you're gonna make mistakes, just say it loud and proud. This is the first time we're all learning this, right? This is the first time for me too. I'm figuring this out as we go. And so I make mistakes all the time. So don't sweat it. Okay, so here we found out magnesium was oxidized. Again, it's because it lost electrons. The oxidation number went from 0 to 2. Okay, let's take a look at hydrogen now. Hydrogen had an oxidation number of 1, and then it ended up with the oxidation number of 0. So did it gain or did it lose electrons? It gained electrons. See? You guys just needed to do 1 and then you guys got it. It gained because it went from positive and it went down. It became a little negative. Okay, it met another Mr. O in its life and it became more sad. And so hydrogen gained electrons, so that means hydrogen was obviously reduced.
What about the chlorine?
Yeah, so we can take a look at the chlorine. If you look at the chlorine, it started at -1 and it ended at -1. So did it gain or lose any electrons? No, it just kind of stayed the same. Chlorine was just kind of hanging out, watching magnesium and hydrogen get oxidized and reduced. So this is going to be your final answer. That is how you can find which one was oxidized and which one was reduced. Yeah, what's up? So it is a spectator. You are writing that, but it's not an ion because both sides of the equation it's not an ion. It's not a positive or negative charge one. So it is a spectator, but we use that term spectator ion only for the net ionic equations, not for redox. That's a great question though. Yeah, so chlorine, you can say it's a spectator. It doesn't do anything. Yeah, what's up? This stuff is what? Yeah, it's being recorded right now. I know you like listening to my voice. All right. Honestly, guys, I think it would be a great way to fall asleep if you can't sleep. Just turn on one of these lectures and then knock out right away. I don't know. My voice is kind of annoying. Okay. If you guys feel confident with these, I'll give you guys maybe about 2-3 minutes. Try this out. This one is a little bit easier for you guys because they already have the charges for you. And again, remember, if there's a charge, you already know the oxidation number. So take a second, maybe about a minute or two, find out which one was oxidized and which one was reduced. My knee hurts too. Day after, I've never felt such tension in your knee once. That'll do that to you. All right, so I'll give you guys maybe another minute to finish that up. Alrighty, guys. So if you guys are finishing up, you guys can kind of zone me out as you guys wrap it up. But let me go over the answers because there are a few more examples I do want to go over. Okay, so this problem was a little bit easier because if you notice, everything is an ion, right? And so if you have an ion, that already tells you what the oxidation number was. So chromium was +1, tin was +4. On the product side, it was +3. And +2. So this one's a lot easier because you didn't need to actually figure out the oxidation numbers. All you needed to do was look at the charge. So let's take a look at chromium. Okay, so it went from +1 to +3. And I know this is the tricky part, figuring out if it lost or gained. But did it lose or gain electrons? It lost electrons. See, you guys are so good at this. Teaching a bunch of geniuses. Okay, we went from +1 to +3. It became more positive. Got rid of the negative people in its life. So if chromium lost electrons, was chromium oxidized or reduced? Yeah, it was oxidized.
For someone so positive, that sounds pretty.
What?
Being oxidized.
Yeah, oxidized is not good. It's how things like rust, a lot of metals rust and they lose their efficacy because they get oxidized. Also, fun fact, you know how we breathe in oxygen, right? So a lot of the things in our body get oxidized and break down. So if you actually think about it, things break down our body because it's slowly burning because of the oxygen. Yeah. Fun fact. So oxygen is bad for you guys. Okay, everyone hold their breath. Okay, now let's look at tin. So obviously if chromium was oxidized, then tin is going to be reduced, right? Okay, and we know that because it went from +4. It was super duper happy. And then it entered Mr. O's AP chemistry class and it became a little less happy. And then hopefully by the end of the year, it'll be negative. Okay, so I can break tin spirit like I will with you guys. That's why I can't wait for winter. You guys will enter this class in darkness. You will leave in darkness. Anyway, I should probably delete that from the video before you're. Yeah, I will. You can show that part to your parents when they ask how class was. Alrighty, guys. We'll do one more. The next one, 4.14, is gonna be like 4.12. It's a little bit trickier. Yeah, I know that they're state of matter notations, but they don't really matter. And so try 4.14 on your own. If you are able to do this one without my help, you are in good shape for both our test and the AP test in terms of the oxidation reduction, okay? Why would I give you candy? Oh, you guys could buy your own candy.
Will you give
So
us
am I.
glucose?
No, you can get your own glucose somewhere else.
You know, you can make cotton candy out of cotton balls.
Like, can't.
You can.
Actually, fun fact, I have taken my urine and made artificial sweetener out of it.
Really? Wow.
Yeah. And yes, I did try it. So there's a compound in your urine called urea, which is why it's called urine. And so you can extract the urea and then you can do a little bit of organic chemistry magic and turn it into artificial sweetener. It's pretty cool.
The urea or the?
Urea. Okay, I'm not like straight up just drinking my pee, guys. Okay, I'm extracting a chemical in my pee.
Just like cotton balls. Cotton balls have glucose, but it's all like tied together. It's like called something really weird.
Some kind of weird polymer or whatever.
It's like all mixed together. So like all the sugars are tied together. So technically cotton balls are made of sugars, but it's just you have to like break down the sugar ties that are.
Dude, you know, I wouldn't be surprised because it does come from a plant. Probably delete that from the video too. Parents are gonna think, who is this guy drinking his urine? Hey, disclaimer, I do not drink my urine. There was one time I almost had to. I was camping. It was snowing. And then I ran out of water. I know it's snowing, but for some reason I thought I had to drink my pee because it was warm.
Snow isn't necessarily like entirely.
It's because it was too cold. Stop talking before you guys judge me too much. All right, I'll give you guys maybe 30 more seconds to finish that up. And then we're gonna start going over it. Yeah.
When we're doing like questions on like the AP test or on the test, is just like the end result like the only thing that matters, or does like
For the MCQ, yes. For the FRQ, no. FRQ, you want to show all your work, or you have to show all your work.
because like what if you're like yes and like
Yeah. So if there was like a question like this on the AP test, and it's like, which one was oxidized? A, B, C. You know, whatever. Then yeah, it doesn't matter. Alrighty, guys. So I'm gonna go over 4.14. If you're still working on it, no worries. Take your time. But I do want to start the next part before the end of class, and so we'll wrap up redox equation, redox reactions with this question right here. Okay. So if we take a look at AS, arsenic, what's the oxidation number for this guy right here? Yeah, 0, because it's in its elemental form, right? AS is it's by itself. Okay. All right. So you should either be finishing up 4.14 or you should be following along, because guys, it's too loud. And like I said, I want to listen to my voice. Okay, I'm gonna go rewatch this video by myself. Anyway, so we got AS 0. Now, if you look at chlorine, Cl2, what's the oxidation number on this guy? 0. Okay, I know it might be tempting to say it's -2 because it's chlorine, right? And you can say, hey, chlorine is a halogen. Halogens are -1, so if there's 2 of them, it must be -2. But if you look at it, there's no charge, and so we can't do it that way. Also, if you look at rule number 1, this molecule is only made of chlorine, one type of element, and so it's in the elemental form, which means that it's 0. Okay, so both of them start at 0. Now, if we take a look at this molecule right here, AlCl3, now we can use that rule about halogens. Chlorine is a halogen. Okay, halogens have a charge of -1, and there are 3 of them. Okay, if you notice, this molecule has no charge, which means at the end, the oxidation numbers have to result in 0. There's only one As, which means the oxidation number has to be +3. Okay, so on the product side, As now has an oxidation number of +3, and chlorine has an oxidation number of -1. Okay, so from here, pretty easy to figure out which one was oxidized, which one was reduced. As went from 0 to +3, so it was oxidized because it lost electrons. Okay, I'm sure that the Cl kind of tripped up some of you guys, which means obviously the Cl was reduced. And that would be your answer. Okay, so if you guys got that wrong, no worries. If you got it right, congratulations. You are better at chemistry than I am, and so you guys are in good shape. All right, so that's gonna be it for redox. We do have one last topic that we're gonna go over, and then after that, we'll be done for the day. But do you guys have any questions? No? Easy peasy? Maybe gonna listen to this later. All right, let's move on to the next topic. Now, this next topic is probably, I would say, one of the most important topics in AP Chemistry because I don't know if you guys took a look at the homework list, but after winter break, the units become kind of long. I know that right now we're doing like 1 and 2 week units, but the units after winter break are like, one of them is like 4 weeks, one of them is 6 weeks. And all that stuff has to do with solution chemistry. And so if you guys don't get this part right here, you're kind of shooting yourself in the foot because we're going to start using this language and doing these types of problems just right off the bat. Fortunately, we're going to start kind of slow here, but I did want to give that disclaimer. Just make sure you guys are following along. If you have any questions, please let me know. I'll be more than happy to stop and explain it. And this is also going to be what our lab is going to be about. I'm actually still debating what to do in terms of the dates. We do have a lab, and I do want to make it 2 days for you guys. So that might push the exam back a little bit more. Okay, so just keep a thumb on it. Again, the exam was pushed back to next week, but it might get pushed back even more. Okay, unfortunately, I know you guys want to take the test quickly. Okay, but let's take a look at this topic. So here we're talking about concentrations of solutions. Now, concentration in chemistry does not mean like you guys focusing really hard. Okay, concentration is a fancy way of saying how, you know how usually we say something is strong, right? If we have a drink, hopefully not a drink, but if there is like a, actually we'll just use that term. Like if you drink something that's super sugary, right? You say, oh, this is like really strong. Like this is really like sweet, or really salty. Like it's very strong, very bitter, right? And it's because it has a high concentration. There's a lot of something packed inside of that solution. There's a lot of stuff dissolved in there. Okay, so that's what the term concentration means. Now, the fancy way of saying it, remember how we talked about solutions, solvents, and solutes? Do you guys remember this at the beginning of the unit? Okay, so if we have a solution, it's made out of the solvent and solute. So the example that we gave was salt water. Okay, in salt water, the solvent is the thing that you have most of, which is the water, the thing that does the dissolving. And the solute is going to be the salt. Now, if we have a high concentration, you have a lot of salt, right? So if we have a glass of salt water, you're going to have a lot of salt dissolved in there. That means it's going to be a high concentration. Okay, whereas if you have a low concentration, you're gonna have the same solution, but there's gonna be not that many things dissolved in there, okay? So high concentration means that you got a lot of solute dissolved in there. Low concentration means you have a little bit of solid dissolved in there relatively, okay? Now the way in chemistry, AP chemistry, that we're gonna measure concentration is gonna be in this thing called molarity. And make sure you guys have this equation written down. You will definitely have to memorize this, but it's pretty easy. Molarity, the symbol is capital M, and it's equal to moles of the solute, right? We know how to find moles, divided by the volume, and it has to be in liters. Okay, a lot of times the AP test and Mr. O's tests will try to trip you up and we'll give you guys the volume in milliliters. Then you got to change it to liters before you can find molarity. Okay, so molarity is just a way that we calculate concentration. The higher the molarity, so high molarity means high concentration. You got a lot of stuff dissolved in there. And then low molarity is going to be low concentration. You don't have much stuff dissolved in there. Okay. So that is how we measure concentration or calculate for concentration. Okay, so we're going to jump right into doing problems with this. But do you guys have any questions about the definition of concentration? I'm sure you guys have probably heard this term before sometime, either in chemistry or just in real life. Okay, make sure you guys have this equation. Molarity equals moles over liters. And if you guys are good, let's jump right into the problem. We're just going to be doing problems until the end of the class period. Okay, so if you look at 4.16, 4.16 asks us which solution is more concentrated. It gives us two different types of solutions, and it's asking us which one has a higher concentration. So what we're going to have to do is we're going to have to use our molarity formula, capital M equals moles over liters, in order to figure this out. So let's look at solution A, the first one. Okay, so what I told you guys to do again is to pull out all the information that we have. So it tells us that our solution is 500 milliliters and it has 21 grams of sodium fluoride dissolved in it. So basically you got a container, it's half a liter, and then you got 21 grams of NaF dissolved in it. Okay, that's basically what it's saying. And so what we're going to want to do is if we want to compare it to something else, because solution B right here, solution B is 100 milliliters and it has 10.5 grams of NaF. Now, we can't just look at these numbers and compare them right away, because even though there's more NaF here, the volume is smaller. And so we can't just right off the bat figure out which one is more concentrated. Okay, because this is just going to be a smaller container with 100 grams or 10.5 grams dissolved in it. So what we're going to do is we're going to use our molarity formula, capital M equals moles over liters. And what we're going to do is we're just going to try to plug them in here. Okay, let's start with milliliters. Are we going to be turning milliliters into moles or liters? Liters, right? Yeah, milliliters, liters. Okay, so if we want to do that, we know the conversion is just to divide by 1,000. Another way you can do it is just move the decimal 3 times to the left. And so 500 milliliters is equal to 0.5 liters. Okay, so again, the conversion factor is 1,000 milliliters is 1 liter. Okay. Okay. Now we have the liters, but now we need to find the moles. So obviously we need to take grams and turn it into moles. This is pretty easy to do. We just need to set up a formula. We're going to put grams of NaF on the bottom. We already know how to do that. And then we're just going to turn it into moles of NaF. Okay, so if I have grams and moles on the same fraction, where am I going to get my numbers from? Yeah, the periodic table, but the fancy schmancy way of saying it is the molar mass. Okay, so we're going to find the molar mass of NaF, and that is what we're going to use to figure out how many moles there are. So if you guys go to the periodic table, the molar mass of sodium is basically 23. And then fluorine is going to be 19. So 23 plus 19 is going to give us 42. So that means NaF is going to be 42 grams per 1 mole. And so what we want to do is we just want to divide 21 by 42, and that's going to give us 0.5 moles. So this is going to be 0.5 moles of NaF. Okay, so from there, pretty easy. We just plug in our numbers. We put in 0.5 moles on the top, and then we put 0.5 liters on the bottom. And so if we have 0.5 on top, 0.5 on bottom, they cancel out, and we're going to end up with 1. And the concentration is going to be 1 molarity. Okay, 1 capital F. I know. Difficult math. Okay, so this solution right here is going to have a concentration of 1 molarity. Okay, so I'm going to give you guys maybe about a minute and a half. Try to find the concentration of solution B and try to figure out which one is more concentrated, solution A or solution B. So do the same math that we did for part A with part B. I'll give you guys maybe about a minute and a half, and then we'll go over it before moving on to the next problem. Oh, you say that. You say that now.
I was gonna say, I can see it already.
Let's make a bet, Molly. If it's that easy, you got to get 100% on the test, or I'm gonna zero out the rest of your tests. Then you can't flex like that and say it's so easy.
I mean, 4.68 is easy.
I'll do it.
All right. Okay, but there's some people that are still learning it, so we don't have to shout and say it's so easy. Okay, you can keep that to yourself. All right, let's stay humble here.
I can see how
It will get very humble. I always do that to you guys. Easy problem, and then I come out of nowhere and slap you in the face. And then on the test,
no, Mr. E.
it's like, have you guys seen that the meme? It's like, in class, 2 + 2 = 4.
Yeah.
On the homework, 2 × 2 is 4. On the test, Bob has 2 apples. Susie has 2 apples. Calculate the mass of the sun. That perfectly describes AP Chem.
That's what I feel about trick questions.
Trig's like that too. Trig is very useful, bro.
Is it?
Trig is physics is all trig and calculus.
I'm so glad I didn't take physics.
Dude, physics is so fun.
I
Physics
took
is so
trig over the summer in college classes, and I completely regret taking that class. It was just like so. It was like, oh, he gave such basic questions for like classwork, and then immediately.
No, but if you take physics, trig makes sense because it's like you can see it, like it applies to real life.
That depends what kind of system my brain. If I'm in physics system, I can see the concept of this. If I'm not on it, I'm on ours.
Exactly, but then like in trig class, they have these ridiculous scenarios that don't make sense. Like John is buying 500 watermelons. Like calculate, I don't know. Yeah, calculate the angle of this right triangle.
It's like that guy. It was like
Yeah,
the
he's
guy-
buying all the watermelons, and it's like, is this Bob from my math class? Yeah, dude, they're so funny.
Carrying all the watermelon.
Alrighty, guys. So if you guys are finishing up, feel free to do that. But let's go over part B, and then we're gonna jump into a little bit of a harder question. Okay. Okay, so we already know that we need to convert the milliliters into liters. So that's just going to be 0.1 liters. Again, you can divide this by 1,000. You can move the decimal 3 times to the left. Either way is cool with me. We got 10.5 grams of NaF, and we just need to do the molar mass to convert it into moles. So divide it by 42. And that should give us, give me one sec, 10.5 divided by 42 is going to give us 0.25. So that means that here, we have 0.25 moles of NaF dissolved in 100 milliliters. So if we just do our molarity calculation, we're going to plug in 0.25 moles on top, and then we're going to put 0.1 liters on the bottom, and that should give you a molarity of 2.5 molarity. Okay, so the second concentration or solution has a concentration of 2.5. So which one is more concentrated, A or B? B is more concentrated because it has a higher molarity. Remember, the higher the number for molarity, the more concentrated it is, the stronger it is. Okay. Okay, so even though B is smaller, it has a smaller volume, it's gonna be more concentrated because within that volume, there's more relative stuff dissolved in it, right? Right, because if I had like a swimming pool and I put like a bag of salt in there, it wouldn't get that salty. But if I had only like a bucket of water and I put a bag of salt in there, it would get very salty. The concentration is gonna be higher depending on the volume. All right, let's try 4.17. I'll leave this up here. What I want you guys to do is I'll give you guys about 3-4 minutes. Try to see if you can find both of them. Solution A is pretty simple. It's pretty straightforward. But solution B is a little bit trickier because we need to do a little bit of more dimensional analysis. But to make your life easier, I'm going to give you guys the molar mass of NaCl. NaCl is 58.44 grams per mole. Okay, so take a second, try to solve this problem. But I know part B might be a little bit difficult, so don't stress too much. As long as you can get A, you're on a good pace for right now. I really recommend for part B that you kind of draw it just to see what's happening. I don't. I can't draw.
I cannot understand my drawing at all.
It's okay, guys. No one's drawings are worse than mine.
I can't draw stick figures.
I have literally had students ask me, Mr. O, do we need to copy down that crap? Referring to my drawing. And I'm like, now you do.
Okay.
Yeah, part B is pretty tough, guys. All right, guys. So if you guys want to wrestle with part B a little bit more, feel free to do that. I'm gonna just give you guys the answer for part A, just because that part should be pretty simple. It's the same thing that we've been doing. And then I'm gonna start going over part B. Okay, so let's I'm gonna delete this real quick and I'll move down a bit. Okay, so for solution A, you should have got a molarity of 1.232 molarity, something close to that. Okay, so solution A, the molarity, the concentration should be about 1.232. If you got something close, 1.2, that's totally fine. Okay. I didn't do anything wrong, right? Okay. All right, solution B is weird. And the reason why I recommend that you guys draw this out is because it's not how it seems just right off the bat. So here, it's easy to say, hey, I got 10 grams of NaCl and I have 150 milliliters of water. So there we go. We can just do 1.5 or 0.15 liters and we can just use the moles and divide it, right? But that's incorrect because if you guys read it carefully, let's just draw a picture of what's happening. So it's telling us that you have a solution that's 150 milliliters of water, okay? And then it tells you that you're gonna add 10 grams of salt, NaCl. Now let's just think about this in real life. If I add salt to a container of water, what happens to the volume? Does it stay the same? No, what happens? It goes up. And so we can't use 150 milliliters because that's not our volume anymore. That's the volume it was before you added the salt. But once you add the salt, we don't have 150 milliliters. So once we have the 10 grams of salt hanging out inside the water, that's not 150 milliliters anymore. And so the point of this problem is to show you guys when you add stuff to water, the volume goes up and we need to calculate for a new volume. Does that make sense?
Yeah.
Kind of weird, right? This is very important because when we do our labs for this unit, this is what we have to keep in mind when we're making the solutions. And actually on the AP test, there are some questions that ask you to write lab procedures. And so you have to keep this in mind that if you add something to water, the volume goes up, okay? So we'll talk about the lab stuff in just a second, but with that in mind, let's start doing our calculations. Okay, so what we need to do to figure out how much the water level went up is we need to use the density of salt. Now it tells us that the density of salt is 2.16 grams per milliliter. Okay, so the density of salt is equal to 2.16 grams per milliliter. And so what we can do is we can take our grams of salt, the 10 grams of salt, and we can use this conversion factor right here to find out how much space that salt takes up. Because if we know how much space the salt takes up, we know how much the water level is going to go up, right? Because if you put the salt in there, water level goes up based on how much space that salt took up in the first place. So we're going to use the density. I have grams on top, so I'm going to put 2.16 on the bottom because I want the grams to cancel, because what I want is milliliters, okay, because that's what tells me volume. And so what we're going to do is we're going to cancel out the grams, and then we're going to punch that into our calculator. So we're going to do 10 divided by 2.16, and that'll give us 4.6. I'm going to round that up to 3. Okay, 4.63 milliliters. Okay, so if we go back to that original picture, basically what we're saying is that, hey, you started off with 150 milliliters of water, but when you put in the 10 grams of salt, the salt takes up 4.63 milliliters. So it's not 150 anymore because you added the 4.63. Okay? And so now our real volume, our true volume after we add the salt is going to be 150 milliliters plus 4.63 milliliters. And so our true volume is going to be 154.64 milliliters, which we need to turn into liters, which is going to be 0.15, and I'm going to round that up to 5 liters. Okay, so this is our volume. Our volume is not 150 because our salt takes up about 5 milliliters of space, okay? And so that was the trick for this problem. And so if you guys didn't get it, it's not a big deal. It's your first time encountering something like this. Just keep that in mind. When you add something to water, the volume will change, okay? And then from here, it's basically the same thing that we've been doing. We have our NaCl, grams. We can turn that into moles. So we're going to do 1 mole on top, 56 or 58.44 grams on the bottom. And that's going to give us 0.171 moles. And so if we want to find molarity for part B, all we need to do is do 0.171 moles on top. We're going to divide that by our true volume. which is 0.155 liters, which will give you a final molarity of 1.106 molarity for part B, okay? So from here, pretty easy. Which one is more concentrated? A, yeah, A is more concentrated.
That makes sense once I read the
Yeah, I told you, it's not easy.
It is easy, but it's just I have to read it twice. to
Molly,
understand.
if you didn't get it the first time, it wasn't easy. And it's okay. This is a hard class. This is new concepts. It's okay if it's hard. It should be hard. Anyway, does that make sense, guys? That when you add something to water, the volume is going to change. All right, so I do want to do one more problem before we finish up the rest of the class period. And I believe the next time we see each other on Friday, we'll be able to finish this unit. And then next week, we'll hopefully be able to do a 2-day lab. And then we'll take the test, I think, about the end of next week, okay? But I'll keep you guys updated on that. Okay, let's move on to 4.18. Okay, so let's scroll down to 4.18, and then this will be our last one today. Now, up until this point, we've been finding the molarity of these molecules that are in the solution. However, we just learned in this unit that if I put ionic compounds inside of a solution, they break apart, right? They ionize. So if I put salt in water, it breaks down into Na plus and Cl minus because water is partially positive and partially negative. That's the same thing for other ionic compounds. And so here, this question is asking us, what is the molar concentration of each ion? So now we have to look at the concentration of each individual ion inside of a solution. So here we have a solution of calcium nitrate. So we got to figure out what the chemical formula is first, okay? So we have calcium nitrate. Calcium's pretty easy. We have Ca. What's the MCI for Ca? What's the charge on Ca usually? +2. Okay, if you look at nitrate, what's the charge of nitrate? -1. So for this chemical formula, how many nitrates will I need? 2. So the formula will be CaNO3 2. This is going to be calcium nitrate because calcium is +2, nitrate is NO3 minus. Okay, but what this does is it tells us that, hey, inside a solution, we're going to have Ca2 plus ions, we're going to have NO3 ions, and they're going to be floating around in there. So in this question, it's going to be asking us, what is the concentration? Now, if I'm going to be using this in the future, but if you see something inside of these brackets, the brackets mean concentration, okay? So you guys can use that. Instead of saying concentration of Ca2 plus, you can just put it in these brackets. Okay, not parentheses, brackets. I don't know, people are pretty strict about that. So we're going to be looking for the concentration of Ca2 plus and the concentration of NO3 minus. Okay, so luckily for us, it tells us the concentration of the entire chemical. The entire compound is 0.12 molarity, and that's for the entire compound. So all we need to do is figure out how many mole or what the molarity for each ion is going to be. Okay, so we're going to set up a fraction. And what we want to do is we want to get rid of CaNO3. So I'm going to put moles of CaNO3. Okay, and the reason why we can put moles down here is because if you remember, molarity is just moles over liters. Okay, it's the same thing as doing this, moles over liters. Okay, so we can cancel out the molarity. Okay. Now, I don't want moles of CaNO3 anymore. I want to find calcium and nitrate. So I'm going to start with calcium. I'm going to put moles of calcium ion on the top. And so here we need to use a ratio. So inside of one molecule of CaNO3 how many moles of calcium are there inside that molecule? 1, yeah, because it's just one of them. So it's going to be 1. Okay, so the molarity of the calcium nitrate is going to be the same thing as the molarity of CaNO3, okay, because we're just multiplying and dividing by 1. So it'll be 0.12 molarity of Ca2 plus. So that's our first ion. Okay, but it's not the same for nitrate, right? Nitrate, there's how many moles of nitrate are there inside of CaNO3 2, yeah, because it's the 2 in the parentheses. So there's going to be 2 moles of nitrate, which makes sense, right? Because we needed 2 nitrates to make the molecule. And so there's a 1-to-2 ratio. So all we need to do is multiply it by 2, and that'll give you 0.24 molarity of nitrate. Okay, so this is going to be your final answer. Your final answer is inside of this solution, you have 0.12 molarity calcium and then 0.24 molarity of nitrate. Okay. So there are different ways of looking at these aqueous solutions of ionic compounds. You could look at the entire compound, so 0.12 molarity of CaNO3 You can look at just calcium, the calcium ion, which is going to be 0.12 molarity of Ca2 plus, or you can look at the nitrate ion, which is going to be 0.24 molarity nitrate. Okay, so just wanted to introduce that to you guys as we wrap up the class. Yeah, what's up?
There'd be a question where we have to like find the amount of grams or like the molar concentration.
Yeah, so the question is, do we need to find, well, we need to find grams using concentration. Absolutely, yes. Absolutely, yes. And we will be doing stoichiometry with this.
Yeah.
So make sure that you guys get a good handle on molarity as we're going through it. If you guys need to review the information before class, make sure to do that, because all we're going to be doing is mixing this up with stoichiometry and then density and then lab procedures, and then we're going to have to calculate the mass of the sun using this. Yeah, what's up?
So we have leaders on the bottom of the layer.
Yes.
What do you think of-
Yeah, that's a great question. So let me break this part down just because the units can get a little tricky. So the 0.12 is just a molarity, right? Let me just get rid of the numbers just so we can look at the units, okay? So if we just look at the units, molarity, we started with molarity. Now, if we look at our equation, molarity is the same thing as moles over liters, right? So if we have moles over liters, we can put moles of calcium nitrate here, and that way they'll cancel out. And then what happens? We get moles on top of liters again. So we get molarity again, and that's how we get those. Yeah. Exactly. And if when you're doing your calculations, if you don't want to change it to moles over liters and you just want to keep it as molarity, but put moles here, that's totally fine because the algebra is still going to work out. That help?
Yeah.
For sure. All righty, guys. Well, that's the end of today's video. Like this video, subscribe to the channel, smash that subscribe button, join my Patreon page and my Discord, and I don't know, whatever YouTubers say. Huh? I'm just kidding. Goodbye, everyone.